Alright, let's take a look at the area of a region between two curves. Alright, since this is area, we do this in 2 dimensions. Even though we haven't went over any 3-dimensional stuff, some of this stuff in this chapter is 3-dimensional. Okay, and we don't have to worry about another axis or anything. We're not going to pull out the z-axis and start doing stuff, not yet. That's usually reserved for the very end of calculus. So if we have 2 curves, it doesn't matter what the curves look like. If you have 2 curves, let's say this is curve F and this is curve G. Alright, and your 2 equations are set up y equals x, or f of x equals x, and g of x equals x. Then if you want to know the area between these 2 curves, I'm going to call this point A and this point B on the x-axis. Then what you can do is find the integral from A to B of the top curve minus the bottom curve. And so you say f of x minus g of x. I mean, you could break this up into 2 different integrals, but that would take a little bit longer. So what I would suggest doing is doing the algebra in here, say f of x minus g of x, then integrate that and evaluate it from A to B. Now, if you don't have what A is equal to and what B is equal to, then you have to find the intersection points. The way you do that is you set one equation equal to the other equation, okay, and solve for x. That'll tell you where the 2 functions intersect. Alright, so you would need both points. You need, because you have to know where to integrate from and to. If you just have one point, you're not going to have the other boundary. So let's look at this example. Let's find the area of the region bounded by the graphs y equals x squared plus 2 y equals negative x, x equals 0, and x equals 1. Alright, so I'm just going to do a rough sketch of these graphs. So x squared plus 2 is going to be a U-shaped graph opening upward because it's a quadratic, and the y-intercept is 2. Alright. Okay. Then y equals negative x. That's a straight line that goes through the origin, has a negative slope, or has a slope of negative 1. So it looks like this. X equals 0. I'm going to do that in another color. X equals 0. This is where x equals 0, and then it's actually, this is x equals 0, the y-axis. And x equals 1, you go out 1 unit, and you draw a vertical line, that's x equals 1. So here's what we want to find. All this in here. And the way this problem was stated was, find the area of the region bounded by the graphs, y equals x squared plus 2, y equals negative x, x equals 0, x equals 1. So you do have to have a little basic graphing knowledge to be able to draw the graph. Now, will I want you to draw the graph? If it says sketch, if I tell you to sketch the graph, then sketch the graph. If not, you don't have to. but you need to be able to picture it because you got to use this to set up the problem. I mean, if you didn't know that the x squared plus 2 graph was above the line y equals negative x, then you wouldn't know how to set up the problem. Because I told you earlier that if you want to find the area between two curves, you say the top curve minus the bottom curve. Now, these two equations here, x equals 0, x equals 1, that just puts the boundaries on your graph, or for your integral. Alright, so the integral of from 0 to 1, top curve minus bottom curve. So the top curve is x squared plus 2 minus the bottom curve is negative x. Alright, so this is going to be the integral from 0 to 1 of x squared minus that negative is going to make that a plus x plus 2. And I just wrote it in that order from highest power to lowest power. That's usually how we write that. Alright, so now integrate. So that's x cubed over 3 plus x squared over 2 plus 2x evaluated from 0 to 1. Alright, so plug in the 1. I'll have 1 cubed, that's 1 over 3, plus 1 squared, that's 1 over 2, plus 2, minus, plug in a 0. Well, plugging in a 0 here gives you 0, 0, and 0, so it's just minus 0. Alright, so that's going to be equal to, let's see, you could make these all sixths. That would be 2 sixths plus 3 sixths plus 12 sixths, right? 1/3, 1/2, and 2. So that would be 17 sixths. So 17 sixths square units, whatever the units may be. Okay. Let me work another example. Let's find the area bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. Alright, so a rough sketch of this graph. This is a quadratic, so it's a U-shaped graph. There's a minus in front of it, so it's opening downward. And the the y intersection point is going to be 2. Right? How do you find the y-intercept? Let x equal to 0. So f of x is the same as y, so y equals 2. That's where it's going to cross the y-axis. What's the x-intercept? For the x-intercept, you let y equal 0. So let this side equal 0. Move the x squared over, plus or minus the square root of 2. So this just helps me graph it. The square root of 2 is like 1.4 something, I think. So if that's 1 unit and that's 2 units, the square root of 2 would probably be about right in here somewhere. So that just gives me an idea of what this thing's going to look like. The U-shaped graph opening downward, and we know it crosses, you know, it plus or minus the square root of 2. G of x equals x, that's, you know, y equals x. That, that needs to, I'm just going to draw it a little bit further down so you can see this. Y equals x is going to go through the origin. And y equals x has a slope of 1, y-intersection point of 0, and then slope of 1. So make a couple points down here. Alright, so that's really close to that, so that may need to actually touch that, but that's okay. I'm just doing a rough sketch anyway. Alright, so the graphs, or the problem says find the area bounded by those graphs. And so I need to just find the integral of the top curve minus the bottom curve. So the top minus the bottom. The top function is 2 minus x squared. The bottom function is x. Now notice what the problem did not give us. It did not give us the boundaries. It didn't give us the intersection points. So if we want to find all of this area here, then we're going to need to figure out what x value is right here. And so again, that's really close, so that may be actually what it's supposed to be, but we'll find out. And then what intersection point is right here. And since it was a sketch, it's really close to that too, but we'll see if that's what it really supposed to be. We can't just guess. You know, just because it looks like it doesn't mean it needs to be. So the way that we can figure that out, if you want to find the intersection points of two different graphs or two different equations, you set the equations equal. Alright? And so if I have 2 minus x squared equals x, then to figure out where these intersect, at least the x value where they intersect, solve for x. So what I'm going to do is I'm going to make this x squared term positive, so I'm actually going to take these two terms and move them to the right side of the equation, because you always want that x squared term to be positive if at all possible. So this would be x squared plus x minus 2 equals 0. See, I'm moving the x squared over, I'm moving the 2 over. Now, the way that you solve for x from here is up to your algebra knowledge. I would suggest either using the quadratic formula or factoring, if it'll factor. And so, if you factored a lot, you can just see right away that will factor. X, that's going to need to be a plus 2 and a minus 1. So that'll give you a negative 2 when you multiply, and that'll give you a positive 1x in the middle. So set each one of these equal to 0. It's a zero product principle. If you ever have factors equal to 0, you can set them both equal to 0 and solve. So that's going to be x equals negative 2 and x equals positive 1. So guess what? That was at negative 2 and this was at positive 1. Okay? My sketch wasn't off too bad. So your bottom number, your bottom boundary always has to be the smallest one, so from negative 2 to 1. Alright, so integrate this and evaluate it from negative 2 to 1. Alright, so that's going to be 2x minus x cubed over 3 minus x squared over 2. I didn't rearrange these from greatest to smallest power. You don't have to. Usually I do, but just to save time I didn't. You want to evaluate that from negative 2 to 1. So first I'm going to plug in a 1. So that's going to be 2 minus 1/3 minus 1/2 minus, now I'm going to plug in a -2. So -2 times 2, that's -4. -2 cubed over 3. So -2 cubed is -8. And there's a negative in front. So it's going to be plus 8 over 3. Then -2 squared is 4. And there's a minus in front. So 4 over 2 is 2 with a minus in front. It's minus 2. Alright, and so let's see. I'm going to get these all in sixths. So that's going to be 12/6 minus 2/6 minus 3/6 minus alright, that's thirds, so it's going to be -12 thirds plus 8 thirds minus 6 thirds. Alright, so that's going to be 12 minus 5 is 7/6 minus -10 thirds, because that's -4 minus 6 is -10 thirds. So it's actually going to be plus. Get a common denominator. That's going to be 7/6 plus 26, or 27 over 6, which is 9 over 2. So 9/2 square units.
We're going to have to use Simpsons to track soil rule on any of these tools.
Alright, so let's look at one more. You know, we couldn't get away from this without doing a little trig. So let's say that I had the function g of x equals cosine of x and f of x equals sine of x. Let's find the area between the two graphs at two consecutive places of intersection. The sine and cosine graphs intersect an infinite number of times in both directions. Recall what they look like. Hopefully you have just a basic understanding of these functions and what they look like. The sine curve does go through 0. Alright, and it goes up, high point, down, low point, up, high point, so on and so forth in both directions. Okay? We know that this place here is 0. We know that it has a high point at pi over 2. We know that it crosses again at pi. We know it has a low point at 3 pi over 2. And we know that it crosses here at 2 pi. Real basic trig knowledge. And that's the sine curve. that would be f of x equals sine of x. The cosine curve starts at a high point, and then it crosses the x-axis at pi over 2. It has a low point at pi. It crosses the axis at 3 pi over 2. It has a high point at 2 pi, and it continues to do that in both directions forever and ever. Alright, so what we want to do for this problem is find the area between the two graphs at any two consecutive places of intersection. So if I could choose any two, I usually choose positive ones, and I usually choose the first ones. That way I know that I'm dealing with the smallest values possible that are going to be positive. At least some of the values will be. So what places are we talking about? The places of intersection. So the two graphs intersect here, and the two graphs intersect here. Okay? Now what x values are those? I'll have to figure out. But if I want to find this area right here, look at the graphs. Which graph is on top and which graph is on bottom? Well, the top graph is sine. The bottom graph is cosine. So our formula here is going to be the integral of the top, which we said was sine, minus the bottom, that I said was cosine. We have to figure out the boundaries. So to figure out the boundaries, you set the two equations equal. This is the classic trig equation that I go over in trig every semester, and I usually tell my students, if you get a chance to see calculus, you'll eventually see this again. Now, they may forget that because they take Cal 1 and then they take Cal 2, so it's not until Cal 2 until they may see this. But if you want to solve this trig equation, if you ever want to solve a trig equation where you have two trig functions, nothing else, not squared, not any powers, not any constants, the first thing you do is you get one on one side, you get one on the other. Well, that's already happened here. Then you either divide both sides by sine or you divide both sides by cosine. What that's going to do is that's going to create a number on one side. So, me personally, I like to deal with tangent more than I like to deal with cotangent. And you'll see what I'm talking about when I divide both sides by cosine. If I divided both sides by cosine here, the left side becomes tangent, the right side becomes 1. If I was to divide both sides by sine, I would have 1 equals cotangent, and I would rather deal with tangent than cotangent. So to solve this trig equation, I just need to know when is tangent equal to 1. Well, it's equal to 1 an infinite number of times, right? But if I want to know the first two places, then it's just going to be pi over 4 and 5 pi over 4. Okay, and that's because tangent repeats every pi. The tangent of pi over 4 is 1. So if you added 1 pi to pi over 4, you'd get 5 pi over 4. You can find other places by just adding 1 pi or subtracting 1 pi as many times as you want. But we figured out this place right here, that's pi over 4. This place right here, that's 5 pi over 4. Okay? So our integral boundaries are pi over 4 to 5 pi over 4. Alright, so now we integrate. The integral of sine is negative cosine, and then I have minus, and the integral of cosine is positive sine, but there was a minus in front, so let's bring the minus down. Integral of cosine is sine. We're evaluating that from pi over 4 to 5 pi over 4. Alright, so this is going to be negative cosine of 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine of pi over 4 minus sine of pi over 4. Alright. So this is going to be negative. Now the cosine of 5 pi over 4, this right here, you can use your unit circle, and remember cosine is the x coordinate, or you just think, what's that going to be? It's going to be in the third quadrant. Cosine is negative in the third quadrant, and the cosine of pi over 4 is square root of 2 over 2. So that's negative square root of 2 over 2 minus, that's going to be negative as well in the third quadrant. So that's going to be negative square root of 2 over 2 minus that's negative square root of 2 over 2 minus square root of 2 over 2. I mean, both of these are positive, but then it's minus in front of both of them, so that makes them negative. Alright, so all of these negatives cancel out. Now, can you add these two together? The square root of 2 over 2 plus the square root of 2 over 2. Think about it like 1/2 square root of 2 and 1/2 square root of 2. That's just square root of 2. Those two together, again, that's going to be a negative square root of 2. It's 1/2 of them and 1/2 of them. So it's negative 1 of them. And then you have a minus here. So it's going to be minus negative square root of 2, or just 2 square roots of 2. You know, if you work out one of these problems finding area and you get a negative answer, you did something wrong, because the area should come out to be positive, because area is positive. So all three of these, we just get a basic sketch of the graph, and after that, top curve minus bottom curve.
All the cosine not in the top curve and not well, I get the graphic on.
As long as both of your functions that you have are y equals x, I mean, we've had f of x, but that's the same as y equals x. That's usually how we deal with functions. As long as that's the case, then we're making these vertical rectangles and we're summing all those vertical rectangles up. Now, if for some reason you don't have y equals x, maybe both your equations are x equals y. So like, you know, you may have x equals y squared, x equals y. If those were your two equations, let me just show you real quick. How do you graph x equals y squared? Well, when you plug in a y, then you get your x. So it's a little different because that graph looks something like this. And then y equals x is the same as x equals y. That graph looks something like this. And so you could find the area between these curves, but what you want to do if you have x equals y, instead of saying top minus bottom, you want to say right curve minus left curve. Alright, and when we do that, right curve minus left curve, we're not making vertical rectangles, we're making horizontal rectangles. I mean, that's not really going to make that much of a difference, but since we do right minus left, whenever you set up your integral, what do we usually put as the boundaries on all of these that we just worked? All of these that we just worked, what are the boundaries? From the x. If you have to set up one that's right minus left, instead of x's, you're going to have y values. Okay? It's the same formula, right minus left. Now, since you do have, or you can have x equals y instead of y equals x, it's not dx, it's dy. You have to integrate with respect to y instead of x. Okay, so let me show you a quick example of that. I know maybe running a little short on time, but I would rather show you one real quick. It's already worked out. Alright, so let's say that up here, if you look at these graphs down here, I have the graph, this is x, g of y is the same as x. This is x equals 3 minus y squared, and x equals y plus 1. That's this and this. Then you set it up the same way. You say right curve, that's this quadratic, the U-shaped graph, minus left curve. Now, when you find the intersection points, you set these two equations equal, and you solve for y to get the y intersection points. So when you set up your graph here, they found the y intersection points -2 to 1. Alright, that's very, very important. If you set up one right minus left, the only time usually you do that is if your equations are x equals y. Then make sure you use y intersection points with your integral. Okay.